module on thin film fabrication. In the last lecture we looked at one of the most sophisticated approach to make thin films, that too to confine in monolayer thicknesses, that is in atomic scale, which we call it as molecular beam epitaxy. Molecular beam epitaxy is one of the most refined thin film fabrication unit that is available both for the industry as well as for basic research. As we saw in the last lecture, the conditions that are used in MBE is not something that we can use practically in today's research conditions because we work with very ultra high vacuum. But normally for us to evaluate any system and to look for new possibilities, new avenues, it is very difficult to maintain a MBE chamber and to conduct a research, and especially in our country. So the best way to look for opportunities in research is to go for much more faster and more friendly techniques. One of the technique is pulse laser deposition. It is actually abbreviated, or people popularly refer to as PLD technique. PLD technique is one of the most used throughout the world for making thin films of any material that is of interest. In this talk, I am going to tell you about what this PLD is all about, and as you would see, it is interaction of laser with matter, and that will actually ablate a material and will help us in making films with proper substrates. So in terms of a definition, pulse laser deposition is a thin film deposition, specifically a physical vapor deposition, because there is not much chemistry involved, and it's also called PVD because a complementary chemical technique called CVD is there, chemical vapor. So this is a complementary technique to CVD technique, where a high power pulse laser beam is focused inside a vacuum chamber to strike a target of the material that is to be deposited. So this is a high vacuum chamber. Usually for normal practices we use 10 power minus 7, but you can also use 10 power minus 11, that is ultra high vacuum chambers. So in this whole episode of deposition using pulse laser, the ejected species, they expand into the surrounding vacuum and in the form of a plume, which we call it as laser plume, and this will actually bring about energetic species which carries atoms, molecules, fragmented molecular species, electrons, ions, clusters. All this they come in essence and reach the surface of the substrate, and at the substrate there is another reaction that is going on which will decide whether you are getting the required film or not. So this is the simple dynamics of a pulse laser deposition. We will see some animation of it in the next few slides. Just to tell you how simple this could be, you shine a laser and through optics you try to converge it. Usually this laser is incident 45 degrees to a rotating target. This target is actually keeps rotating, and as it rotates, laser comes and strikes, and this is kept perpendicular. The substrate is kept perpendicular to the rotating target. So whatever that is removed from the surface of the target is now going to come and reach the surface of the substrate. So once the substrate is kept at high temperature, then you can actually make the desired film whatever you want. So this is the simple protocol. What it involves is a vacuum chamber and some optics, and then whatever is happening inside is to do with the vacuum chamber. So it's a very simple protocol compared to molecular beam epitaxy. in terms of achieving vacuum and in terms of handling the instrument also. The removal of atoms from the bulk material is done by vaporization of the bulk at the surface region in a state of non-equilibrium and is caused by a Coulomb explosion. So we will look into some of the requirements of what really happens at this plume and target surface. So what exactly comes out in the form of ions and electrons and molecular species as a laser plume is nothing but a Coulomb explosion. In this, the incident laser pulse actually penetrates into the surface of the material within the penetration depth. So when it is the interaction of a laser plume or a optical beam with the solid material, therefore how much of this light or the photon can enter into the solid determines what will come out. So if it doesn't penetrate high enough, then you would hardly see anything coming out. But if the penetration depth is quite deep, then you will get almost all the species that is required out from the surface of the target. So this dimension is actually dependent. The dimension meaning the penetration depth is dependent on the laser wavelength and the index of refraction of the target material at the applied laser wavelength. So in this, caution to be taken that it should be a material which will absorb your laser plume. If it doesn't absorb your laser light, then it will not emit. Therefore, your optical coefficient of your material is important. In essence, you cannot ablate a insulator that easily as much as you ablate a metallic material. So this becomes a inherent problem, especially because the penetration of the laser light is the governing factor here. So therefore it puts some quantum restrictions on to the sort of materials that you can use with these. So it is typically in the region of 10 nanometer for most materials, meaning the penetration depth. So if you can achieve this much, then you can actually bring about the surface of the material in the form of a plume. Typically this is how laser PLD will look like. This is the vacuum chamber as you see here, and at the rear side you see excimer laser that is housed, and in between you see this glass windows, mainly to shield from the radiation, because what you are pumping is actually UV radiation from excited krypton fluoride, and this is actually giving a UV radiation of 248 nanometer wavelength. Because you are using ultraviolet radiation, it is important that you shield it. Therefore this is not a very friendly one, and care should be taken, because you wouldn't see this UV radiation coming out of the laser. Therefore, out of curiosity, one should not even peep into the pathway, because that can easily burn your eye, and the person can even go blind if he takes one shot of this UV light, because it is highly monochromatic and high power laser. Therefore, it is always important to have some protocol where these radiation effects are minimized so that the handling becomes easy. So this is typically a PLD setup. In any PLD lab you would see the vacuum system, then the optical arrangement bringing the laser light into the vacuum chamber, and then of course the laser. Typically when you are trying to do reaction, what you would see during the PLD deposition is some sort of a flash like this, which means the plume is actually coming with very high intense colors, and the color can actually tell you whether you are really depositing the right material under right conditions or not. So it can be as friendly as it would be if you get used to the laser plume. So typically during the process you would see some sort of flashes like this. So that's how it goes. Now the next question is why we need to take PLD so seriously when you have a more refined setup like MBE. But we should also know that research is not just limited to the efficiency but also to the economic considerations. Any lab can easily afford vacuum deposition chambers where you can make polycrystalline and amorphous materials. If you look at the cost, this is actually in Hong Kong dollars, but nevertheless it just gives you how simple a vacuum system can be, which involves thermal evaporation. Whereas if you go for sputtering, it's almost 4 times costlier than a thermal evaporation technique, but again you can play around with polycrystalline films. The next to transcend is laser PLD. Laser PLD is almost of the same sputtering cost, but then you can actually play around with single and multi-phase compounds or thin films. But there is a difference here. Beyond this, whatever you see, those are very, very costly equipments. CVD, for example, chemical vapor deposition, and molecular epitaxy, they are of a higher value, but they usually guarantee epitaxial growth, meaning the film will be always single crystalline. You won't see any polycrystalline phases. Therefore, to get a single or a multi-phase product, you need to choose what sort of deposition technique that you would look for. For depositions involving very high areas, large areas, usually we go for CVD. That's one of the reasons why chemical vapor deposition method still stands as a special case amidst all the other physical vapor deposition techniques. So what really brings the divide is not just the cost, it's also the sort of final product that you are looking for. Either it is a semi-epitaxial growth or a epitaxial growth. So epitaxy is the underlying word. Therefore, certainly this is different from MBE. As I told you in a MBE chamber in the last lecture, MBE chamber is usually tagged to other characterization techniques like reed, magneto-optical Kerr effect, lead and atomic energy spectroscopy, and also to a STM. But PLD instrument is not necessarily interfaced with all these other techniques, in the sense you can have the luxury of breaking the vacuum and taking the material out for characterization. So that way it is more friendly, you can play around with a variety of materials. But in MBE you never get to break the vacuum, so it is always inside the vacuum chamber. Therefore you need to circulate your sample from the processing chamber to characterization chambers. Again you clean the crystal, again you go into this. So it is a loop. But in PLD you can actually, after this you can come out and do X-I2 measurement in a AFM or a STM chamber. You can do a X-I2 measurement on a lead chamber. So this gives a flexibility to play around with different systems. One of the pioneers in this field is Professor Venkatesan, who actually started the application of oxide thin films using PLD. Especially he was the first one to demonstrate how a high temperature superconductor like yttrium, barium, copper can be made as a thin film for device applications using PLD as a convenient route. Therefore I just wanted to show this setup, and this is a good article that has come out in APS magazine. So pulse laser deposition offers a very fast route to prototyping any thin film coating. So if you want a quick study on any complex material, the best thing to adopt is PLD. Just to give you a clue why it can be versatile, is that this is a bismuth strontium calcium cuprate, and this is a material which shows high temperature superconductivity above 130 Kelvin. And if you look at the crystal structure, you would see the copper oxygen sheets and then the barium bismuth and strontium oxide layers which are sandwiched by copper oxygen planes. So this is the one single unit cell of this bismuth copper oxide cuprate. This is one unit cell with so many layers, and it can be effectively fabricated using pulse laser deposition. So a complex unit cell, but PLD will exactly bring about the same arrangement. So therefore PLD has a lot of attraction. Other commercial instruments like PVD is one company which brings about, and this is one of the PLD chamber that they market. You can see the complexity of this, and typically the target of the material which you would like to deposit as a thin film is mounted on a sample holder like this. What you see here is nothing but a used target of a particular material which has gone through several depositions. So you would see the imprints of the laser beam interacting with the material, and several times it has been used for ablation. But not only that, you can also use multi target holder. So if you want to make a complex material like what I showed in the previous slide, bismuth, strontium, copper oxide, you can even start with individual oxides and try to judiciously make such a layered compound, and that's why you have different target holders with different fashions. So you can actually mount more than 6 or 7 at a time, and with computer monitoring you can switch between these targets and try to make complex oxides. All these are possible in a PLD chamber. So the inside part of the chamber essentially will look like this. You can see here these are the rotating wheels. Depending on the choice material, you can keep switching between two targets, and therefore this is how the deposition chamber will look like. This is another example of how PLD can be made, can be used for a superconductor, and you can see here several stackings of this superconductors can be made. This is IPCO, which is coated and then capped with ceria, then praseodymium cuprate, and then LaLO3 as substrate. So this is a device configuration. All this can be achieved with the same chamber with different target carousel. So if you have 6 or 7 targets mounted, you can realize such a complicated device stacking. So in terms of versatility of PLD, they have non-volatile targets, and multi-component targets are possible, and multi-targets for multi-layer or alloy films we can try to achieve using PLD, and this is also operated under any ambient gas. For example, you can use argon, you can use oxygen, you can use nitrogen, you can use any other helium for that matter. Any gas can be used depending on the sort of system that you are going to use. And another thing, with the number of pulses that you are generating, you can try to control the thickness of the thin film, and we can also control the substrate temperature. For example, if you want to prepare polymer films, then you can prepare at room temperature. If you want oxide films, you can prepare at 800 degrees C. So you have flexibility to play around with the substrate temperature, and deposition rate can also be fine-tuned. Disadvantages are, if you are trying to transcend this, to larger levels for large area depositions, it's not possible. So even to make a 6-inch wafer, it is very difficult, but people are aiming at such large area depositions. Because of the energetics that is involved in this reaction, usually you end up with some sort of particulates sticking, meaning some chunks of material can also be thrown out along with a very good layer growth. Therefore, this can become a problem. For this, off-axis PLD has been suggested, and target surface modification can happen, especially when your laser is hitting the target with such a very high energy. There may be congruent melting at the surface region. Therefore, if your material is not sensitive, or if it is very sensitive, then it can go into a liquidous phase and it can change the property. So such problems are inherent when using this. Some applications we can make ceramic films. When I say ceramic films, it's not about clay and pottery. We mean the superconductor as a ceramic. We can make piezoelectric as a ceramic, nitrates as ceramic. So several electronic materials termed as ceramics can be made. Hard coatings like diamond-like films, carbides, nitrates can be made. Alloys and multi-component systems can be made, including manganites for magnetic application. Multi-layers can be made, super lattices or heterojunctions can be made using this, and graded layers can be also be achieved. By this way, you are almost covering entire spectrum of compounds. Whatever you want, you can actually translate this into a thin film. So that way, it's a very friendly technique one can look at. Coming to the energetics and what exactly happens inside the vacuum chamber, there are 3 regimes that we need to take into consideration, and each one is a dynamic in itself. Therefore, to handle this dynamics is the proficiency that is required. So if we start as a beginner, we need to understand that we should become more friendly with all these 3 regimes, and one should have a feel for what this regime 1 will do on regime 2 and then will affect on regime 3. So a comprehensive understanding of what is this dynamics is what is needed to exploit this deposition process. Regime 1 is laser target interaction. So laser is coming, interacting with the target. What are all the things that we need to know? Regime 2, gas phase transformation. So this is nothing but the Plume dynamics. So what really happens with the Plume? What happens, suppose the Plume is going like this. What will happen if the Plume is actually narrowed down like this, like a bullet? So the shape of the Plume and the color of the Plume also will control the final stoichiometry. Regime 3 is deposition and film growth. Now something is coming from the Plume and I am depositing it. What should be the control? How I can get the best film that I want? So all these 3 are important. In the PLD process, especially when we talk about laser target interaction, there are 2 things that we need to understand: the thermal process and the non-thermal process. Thermal process, where you have the energy of your laser light, that is EH nu, the energy is less than the binding energy of your substrate material. For example, you are actually trying to break the bond and bring out the solid material in form of ion, molecule or atom or as electron. So many things are actually going to come out in the form of a Plume, and when it is happening, we need to know whether the EH nu, that is the laser light, is sufficient enough to overcome the binding energy. If it is not, then if it is less than EB, then there is thermal equilibrium and there will be a Maxwellian velocity distribution, and in that case the whole growth process can be very different. The other form is non-thermal process. In non-thermal process, you actually have 2 situations. One is a electronic process and another one is a bond breaking process. Usually in the material science, we give more attention to bond breaking process, because you know the material and you know whether it is a ceramic, whether it is a polymer, or whether it is a metallic material. So you know how much of the binding energy each material is associated with. Therefore you can try to transcend that by increasing the laser energy. So if your laser light is EH nu, which is going to be far greater than or equal to EB, then you can think of desorption of surface atom through bond breaking. For polymers and large molecules, bond breaking changes the molecular structure, resulting in a sudden change in volume or micro explosion and blast wave ejecting surface atoms. So you need to have some amount of idea about the binding energy of the atoms and molecules in the target, so that you can essentially maneuver or you can alter the laser light. So congruent evaporation and subsurface superboiling, these are parameters that we need to keep in mind, because your laser light essentially will bring about knocking of this material, and because of the continuous heating on the target material, there will be some amount of melting and boiling that will be happening at the junction. So we need to know what sort of energy that is coming out when laser light is interacting with your surface. For example, if you use carbon dioxide laser, the wavelength actually will generate only 0.1 EV, and that is not good enough for ablating any of your inorganic material. So what you do, you try to use NdAg. NdAg is another laser material, and it actually gives in more than 1000 nanometer wavelength, and corresponding to 1.17 EV. But you can actually use filters to generate second, third or fourth harmonic ones. Thereby you can increase the energy of your laser light. So that way you can go up to 4.66, and this goes into UV. So when you are using fourth harmonic, you are actually getting a UV light from NdAg. So this is a high power laser when you are operating at 266 nanometer. And then you have excimer lasers. Excimer lasers, xenon chloride is well known, but mostly it is krypton fluoride which is used, which is 248 nanometer. And then you can also use argon fluoride and fluorine, but fluorine, because of the handling hazard, it is not usually recommended in the commercial lasers, but argon fluoride and krypton fluoride are used, where you can see very high power laser efficiency is achieved. So if this is the energy that I get from the laser source, then I should also know what is the EB governing this material which I am planning to ablate. For example, if it is an organic material involving carbon-carbon, single bond, triple bond or double bond, those are actually pretty strong. The binding energy or EB is of the order of 8.7 for carbon-carbon triple bond, and carbon-carbon double bond it is 6.34 EV. So to break this bonds and bring it out, you need sufficient energy. So you need to have this idea, and also you would find out that it is the binding energy is more for ionic materials than covalent, than even metallic materials, but those which are governed by van der Waals force and hydrogen bond, those can be easily broken. So from this numbers we can see that depending on the choice of the laser, you can actually try to extend the ablation of material from ionic material down to organic, depending on the choice of the laser source. So when you are thinking about a target to substrate, there is a gas phase transportation. Here is your target material, light laser has come, it has hit. Now everything is going into a gas phase transportation. So everything is being moved and typically the translational energy is of the order of 10 to 100 electron volt, and that's what makes this whole process very rich, because the ions and the molecules and the electrons, atoms, everything is carrying very high kinetic energy as they are rushing to the substrate. So in this there are two different conditions. One is thermal and non-thermal conditions, where you can see the gas phase transportation can actually vary quite a bit. Look at the shape of this plume and look at the shape of this plume. So depending on the shape, the energetics of this transportation will change remarkably. So in the thermal case, it is actually a cos theta dependent, whereas in the non-thermal case, you would see its power factor is associated with it. It is cos n to the power n theta, where n is always greater than 1. So in typically it is of the order of 10 to 25. Therefore, depending on the plume, you can actually modify the whole growth process. So one should have an idea just by looking at it whether your plume is really good or not. Otherwise you are heating somewhere and nothing is arriving at this substrate. So you have to have an idea how to maneuver this gas phase transportation. Okay. So once this plume is directed and it is reaching the substrate, then the next thing that we need to understand is the nucleation and growth of the film on the substrate surface. The nucleation process and growth kinetics depends on several parameters. Growth parameters: one, laser parameter, I have touched upon it. The laser fluence or the laser energy is very important. Therefore you need to know what is the optimum laser energy that you need to use. In fact, as there is a calibrant which can be used, a calibrating instrument which will tell whether you are getting the required laser energy before every deposition, because continuously, since the coating is done, the optics can also take this ablation and it can filter the laser light from reaching the source to the fullest extent. Therefore it has to be calibrated. Then surface temperature, suppose you are making a high temperature superconductor film, the substrate also has to be elevated to a particular temperature for the film to grow and show a crystalline phase. Otherwise it will be amorphous phase and it may not show even conductivity. And the substrate surface also is very important. We cannot simply mount anything. Even if you are mounting a silicon or any other single crystal, pre-treatment has to be made. It should be highly uniform and it should be treated properly before the deposition is made. And the background pressure, as I told you, the plume dynamics depends on the pressure. Suppose I am using oxygen, whether I use this deposition at 10 millitorr or 100 millitorr or 400 millitorr oxygen pressure, that will decide whether the film is going to be fully stoichiometric or not, if we are aiming for a oxide film. So background pressure is also important. In PLD, just like the way I emphasized in the earlier lecture on MBE, the growth mode also proceeds similar to molecular beam epitaxy, in that it can be a step flow method, it can be a layer by layer growth, or it can be three-dimensional growth. As I told you, pulse laser deposition, because of the high kinetic energy that is involved in this plume dynamics, usually you get the layer by layer growth, which is the most favored deposition growth mode. But 3D growth mode brings about a lot of roughness in the film, and therefore that is not desired. So we need to have an idea about how to grow a layer by layer growth. The next animation slide, you can see we can monitor the film growth using reed oscillation. As you would see here, every maxima in the reed oscillation corresponds to one full coverage of the layer, and every minima corresponds to almost half the coverage of the thin film. So this is what we mean by layer coverage. Therefore, if you aim for such deposition, then you get a flat terrace, and that is more desired for making even heterostructures. So one should always look for a situation where you can actually get this maximas corresponding to coverages. Typically you wouldn't expect this sort of coverages, but what could happen is sometimes in the initial phase there could be a 3-dimensional growth, and then it can proceed to a 2-dimensional coverage. Therefore we need to have some optimization before we try to go for several layer of stackings. So we need to do an individual calibration if we are going for several multi-target systems. So in such cases some calibration is needed as to evaluate whether a 2-dimensional growth is happening. This is another view graph which tells us the distance between the target and the substrate can also play an important role in getting the right type of material. For example, if you allow the laser plume to converge like this and then it hits the substrate, then you would see if we adjust this distance between the target and the heater where the substrate is mounted, you would see that the microstructure of the films changes systematically, and the microstructure of the film can be greatly influenced if you are going to introduce a mask between the plume and the substrate. So the distance between target and the substrate can also play an important role, because in this case you are actually cutting half the plume, in this case nearly 3/4 the plume, in this case you don't cut it at all, in this case you cut it half but then let only the mask do the job. Therefore the microstructure of the film can be maneuvered by this distance, so it's very sensitive that way. And we should also understand when the plume has reached the substrate, again the sputtered flux will go back and it will also create a thermalized region in between. So the incoming plasma will be actually encountering a thermalized region. So the gas pressure that you use during the deposition will actually try to clear up this thermalized region. Therefore care should be taken to get the right type of plume that you desire. In fact, those who are familiar with this art will easily make out whether you are really doing the right deposition. For example, the oxide plume for manganite has to be blue, whereas for high temperature superconductor it has to have a crimson red tinge to it, and if you are looking for titanium nitride, then it has to have a bluish tinge. So just by looking at the plume itself, one can decide whether you are doing the right deposition with the right parameters or not. So it can become that friendly provided we know how to control the plume dynamics. Now I will take you through some examples briefly, if possible on a greater detail in the subsequent lectures. First let me start with the animation of how various layers can be coated using PLD. You can see here we are actually switching between two targets, and this can be done, and what you see as a laser light is nothing but the read incident beam, which is going to monitor whether you are hitting it right. So this read oscillations, as you can see in this cartoon, the read diffraction spots are there, and those spots will tell you whether you are really doing a layer by layer oscillation. As a result, you can see here this sort of oscillations are coming depending on the way you are trying to coat the material. So you can make these stackings alternately using a read oscillation, and that way you can control and make a periodic deposition of superconductor. In this case This is your SrTiO3. Then you can put this green patch is nothing but your barium cuprate, and then you can put yttrium cuprate and barium cuprate. You are essentially imitating a unit cell, and you can do that by taking a separate target of BaCuO2 and a separate target of yttrium CuO2 and keep on making this repeat deposition, and this can be monitored using the read oscillation. Such sophistications are already available in today's commercial PLD instrument. Now if you look at the range of materials that you can make out of this deposition process, you have yttrium, barium, copper. These are all the superconductors people have used as early as 1987. So PLD became very prominent only after the discovery of the superconductor. Then you have the oxides, silica can be made, carbides, nitrides, even carbon and C60 can be made, diamond like carbons can be made, polymers like polyethylene, PMMA can be made, metallic systems, alloys, multi-layers, borides can be made out of this. So if you look at the spectrum, almost you can achieve any sort of material as a thin film. One of the example that I want to show here is Lu2O3, which is done in our own group. Lu2O3 grown on several substrates. Why Lu2O3? Because this is a very important molecule for tunable laser materials. If you can dope with, for example, cerium, then this can be used for tunable laser material or as new phosphors. So there is a lot of challenging work going on in Lu2O3, but the point is to make a single crystalline film, it's very difficult. And as you see here, using PLD we can make a single crystalline film of lutetium oxide, and this is the optical measurement in transmittance mode. And you can see here, you can make a very nice quality Lu2O3 film, and look at the transmittance level. It is nearly 90% transmittance, which means it's almost a transparent electrode sort of thing. So you can make such clean material on a variety of substrates. For example, here we have used yttrium stabilized zirconia. Why we use yttrium stabilized zirconia? Because the lutetium oxide cell constant is exactly twice that of yttrium stabilized zirconia, which is a cubic material. So in the next slide I will show you how good quality film we can make. But it's also surprising that you could see lutetium oxide grown on silicon showing such high laser action. This is the laser that is incident on the film, and this is the lasing light that is coming out of Lu2O3, which is grown by PLD. Incidentally, the full width and half maxima of this emission peak is only 1.2 nanometer. So if it is showing such sharp emission, then you can see the lasing action of such emitting stuff. This can be made out of PLD, and this is a good TM image that tells how PLD can clearly help you in growing epitaxial films. For example, if you see the electron diffraction pattern of YSZ, this is the substrate region and this is the interface region along this line, and this is the Lu2O3, which is cerium dope, and these are the lattice fringes. What you see as stripes are the lattice fringes. In other words, those are the atoms. So if you look at the interface here, there is no distortion between this lattice and this lattice. In other words, if you look at the diffraction spots, between two diffraction spots you see repeats. So they are exactly matching, and therefore you can easily grow Lu2O3 on yttrium stabilized zirconia because they have exact lattice matching. One lattice plane is equal to half of the lattice plane of YSZ, therefore it's exactly able to sit on YSZ and grow as a epitaxial layer. So this is one convenient way where you can realize highly oriented epitaxial films of such complex oxides. Another example is that of manganite thin films. I have discussed about this manganites extensively in the next module, but I will show you only the study related to thin films. As you see here, if you keep on doping ruthenium in this LaPbMnO3, a strong ferromagnetic loop is shown with 10% ruthenium, 20% ruthenium, 30% and 40%. Still you can see a very strong ferromagnetic signal. However, if you look at the conductivity data, as you increase the ruthenium concentration, you can see there is a upward in resistivity. That we don't know whether it comes from the bulk phenomena or whether it is due to the antiferromagnetic interactions that are competing in this set of molecules. So there is no way you can clear this doubt other than making thin films, because in thin films you don't bring in the grain boundary issue. Therefore, if there is any upturn in resistivity, you can directly correlate that to magnetic phenomena. So that way, if you are only studying bulk, then you cannot resolve some of the issues for which PLD can be a very good system to work with. You can make films of very high quality, and this is again HRTEM image, high resolution transmission electron microscopy, which gives you idea about the interface. As you see here, every dot here is nothing but a unit cell or the atomic position of lanthanum oxide. This is the lanthanum oxide picture, and this is the manganite film that is grown on the substrate. As you can see here very clearly, there are no two different spots. If there are two different spots, then that would correspond that it is not growing epitaxially. But if you magnify these spots and see here, you can see two spots together in each spot. Whatever you see here is nothing but two spots, and that one coming from LaO and one coming from manganite film. What it means is they have very close matching, and therefore they are epitaxially able to grow. And if you look at the interface here, this region seems to have little bit of interfacial problem, roughness, but you can see here there is no change in the interface ordering because of the lattice mesh. They are able to grow epitaxially. So highly oriented manganese film can be made using PLD, and this is another example by Krebs group in Germany, where they have used PLD for thin film deposition of PMMA. This is polymethyl methacrylate. As you can see, the IR is matching. TEM of a polycarbonate film can also be made embedding nanocrystalline silver grains, and you can also see that you can get predominantly oligomer based PMMA using this PLD. So you can extend this to that. But there are some issues that we can try to address as we use this process extensively. One is droplet effect, another one is the issue of large area deposition. There are several refinements that have come on the way just to help us to increase the utilization of this method. For example, to avoid the droplet effect or to minimize on the grain boundary issue or roughness, there are several schemes that are proposed. One is you can use the this is the typical setup where laser comes, ablation, and then that goes and deposits on the substrate. But there are some refinements made. For example, we can have a gas pulse which is actually crossing the ablated plume, which can bring down on the heavier atoms or chunks arriving at the substrate. Therefore, you can reduce on the roughness of the film. There is another way to do that. You can use RF plasma here. So one can use RF plasma, which will also interfere with your laser plume. As a result, you can try to minimize on the roughness. So this sort of refinements can be made, and there is another way one can do it. For example, look at the growth of germanium on germanium 001. Assist group in Cambridge have attempted this. This we call it as homoepitaxy, because you are growing the same material on the same single crystal. Therefore, it's called homoepitaxy. And look at the dynamics here. If I use MBE, if I use PLD with the high kinetic energy, that is 300 electron volt, and if I use PLD but with a very less energy, then you can see these are the thickness of the films: 28 nanometer, 30 nanometer, 27 nanometer, almost same thickness, but you can see the microstructure vividly changing. What does it mean? This can greatly affect the epitaxial growth of your film, and this cartoon tells us that PLD with low threshold or with very less kinetic energy comparable to thermal evaporation, the epitaxy actually breaks down even with just 20 nanometer thick film, whereas the next one to break down is molecular beam MBE based film, whereas the PLD with very high kinetic energy can show a very high epitaxy even up to 100 nanometers. So that is the advantage of the PLD process. And another refinement has come. This is called as Aurora PLD method. What they are doing here is they are trying, this is the typical PLD process, but what they have inserted here is near to the substrate they have placed a magnet, and you can see once you do that, the zinc oxide plume that is reaching the substrate, the plume dynamic changes here. You can see plume is actually traveling, but it is not clearly reaching the substrate here, whereas in the case of the Aurora method, where they have kept this magnet near to the substrate, the plume is actually reaching up to the substrate. Therefore, the plume dynamics changes. So in effect, this magnet is actually kept like a reflecting mirror. So the electrons which are also going, they get reflected and they transfer the kinetic energy to the atoms and species. As a result, you have an activated deposition process. So if you actually look at the quality of films from a conventional PLD, where you have the PL efficiency is noted here, it's twice the PL efficiency for a Aurora PLD approach, and if it is done in argon, you still feel 3 to 4 times enhancement in the PL intensity. As you know, the band-to-band emission of zinc oxide actually is pronounced with a 380 nanometer peak, and so even though you are getting a good quality film, yet the PL efficiency suffers when you are using a conventional PLD. So you can bring about lot of modifications, and that is also reflected in the carrier density and mobility. Therefore, we can try to fine tune on those issues also. There are some links which can give you more idea on the application of PLD, but I stop here, and we will try to give you some more examples in the bibliography, so that you can refer to other processing parameters which can be taken into account to get a improved film growth, and also to extend this process to variety of other materials.